Good afternoon, everyone. We are very happy today to have Sunny Itzhaki from Tel Aviv, if I remember correctly. And he will tell us about string information and black holes. So please, Sunny, take it away.
Thank you. Yes, it's great to visit, even if only virtually. But well, in any case, it's great to give this talk. So I'll talk about work that I've been doing with Amit Givon for many years now. About, well, the title is taken from one of our papers, but we'll see. Okay, so what am I doing? Yes. So for many years now, there is this general feel that we are missing something very deep about information when we think about black holes. And in general, I would say two types of approaches to the problem. One is to try and figure out if there is a new rule when it comes to quantum information in quantum gravity, and there was some progress about this in recent years with the island and things like that. And another approach, which is the one that I'll be pursuing here, is to see what string theory can teach us about the subject. So basically, what we've been doing for the last decade is to, well, if you wish, try and listen carefully to the best of our abilities to see what string theory is trying to tell us. And the main, I would like to state the main message of the talk at the very beginning, and the main message is that information in string theory is quite non-trivial. There are situations in which states that semi-classically look completely different are actually exactly the same, or if I want to be a bit more precise, they are two components of the same states, of the same exact state in the CFT. And what I would like to argue is that this is very important when thinking about information in black holes. And but in a sense, all of this goes back to what people like to call the FZZ duality, the Fadeev and Zamolodchikov's duality. So what I would like to do is to start slow and spend some time on the FZZ duality, and eventually we'll see what it means about black holes. Okay, so this is the plan of the talk. So let's start with the FZZ duality. The FZZ duality, we can think about it in the following way. So here we have a cylinder, and there is a linear dilaton in the radial direction. So this is weak coupling, and this is a strong coupling. Well, we can, well, there are some facts about the relation between the slope of the linear dilaton and the radius of the cylinder. They are a bit different when thinking about the supersymmetric case versus the non-supersymmetric case. But one thing that is general is that, well, when K is large, then the slope is small, and K will be related to the number, if you wish, of NS5 points that we'll talk about, or the level of the SL2 modeled by U1 theory. Okay, so so this is our starting point, the cylinder. And now we can basically chop. So this is a strong coupling regime, we would like to chop it off so that the theory will be well defined everywhere in perturbation theory. And there are two ways to do it. One way is to replace this part by a cigar geometry. And the other one is to add a sine Liouville potential that basically block things from going to the strong coupling regime. So this is, well, a version of the Liouville story that involves also excitation in the angular direction. So so if we think about what it looks like, then the cigar means that I start with the cylinder and I cut it off. There is a certain point, which is that point, the tip of the cigar, where the string coupling becomes obtain its maximal value. And there it is weakly coupled. And the other possibility is to add a potential. So here I'm just plotting a potential. And that potential prevents things from going to the strong coupling. So you throw something and it goes back. So so these two ways of chopping off the strong coupling regime look very different. And indeed, if you think about the kind of operator or 1,1 operator that you have to add to the story to go from ear to ear, then at infinity, the tail of this operator goes like exponent of minus phi times q, while the sine Liouville deformation is an exponent that goes like is a deformation that goes like an exponent of minus phi over q. So clearly, especially when q is very small, and this is the region that we'll care about the most, then clearly this tail is much softer than this tail. So these are very different deformation. They are very different in this region, as we can see. But even if I sit at infinity and I just, I'm an observer that lives at infinity, then these two deformations are different. The FC residuality is the statement that they are actually the same. And originally, the way that people like to think about it was that, we have, it's an example of a duality in which we have two descriptions that appear to be different. And as usual in dualities, when one is good, the other is bad, and vice versa. So indeed, they look very different, but they look also different at the more conceptual level, because here I've added a potential. So if I throw a wave packet with a certain energy, it will reach a certain point and it will bounce back. If I'll increase the energy, it will go deeper and it will bounce back. And here there is an end to that story. So it looks very, very different. And the question, of course, is what does it mean? Now, if Q is small or if K is large, then you would think that this description, the cigar description, is the proper description. This is the more natural description. And vice versa, namely, if K becomes of order 1, then you need to, only then you need to worry about the sine Liouville. But the situation is actually much more interesting than that. And you can think about the following, if you wish, experiment to illustrate that. Now, suppose that I have this cigar and I throw a certain wave and I get it back. Now, if I want to do this in string theory, I want to be on shell, so I have to add a time direction to do that. So let's do that. Let's add a time direction and probe this geometry. So P, this would be the radial momentum, L is the angular momentum at infinity, and I throw this wave and I get it back. Now, at the semi-classical level, the reflection coefficient gives the phase shift at high energy, and this phase shift, basically, if I go to a very large energies compared to the curvature of this cigar, then I see the usual phase shift, which is basically the -1 to the L effect. And then there are corrections. And if I increase the energy, then I see, as I keep increasing the energies, then these corrections become less and less important, and I see the trivial reflection coefficient that is associated with the fact this region looks just like R2. So this looks like R2, and the angular momentum becomes an angular momentum here, and this is this phase shift that we get from this angular momentum. Now, if I add the perturbative alpha prime correction to the story, I get exactly the same thing. But if we add non-perturbative corrections, then something very dramatic happens. Well, you get this extra phase shift, and this is an exact result that was obtained by Teschner, which states that all the non-perturbative corrections, they take this form, and if I go to very high energies, then I get a phase shift that keeps on going indefinitely. So in particular, this fits extremely well with the Sine-Liouville point of view, because in the Sine-Liouville point of view, the potential keeps on growing, but if I increase the energy, then I can probe more and more of the strong coupling region, so I can go more and more to the left. And this is exactly what that equation is telling us. So this is a story that is not terribly important for our talk, but the conclusion is that we see it's not that we have either the cigar or the Sine-Liouville, but that we have both of them. And actually, there is a very acute implication of all of that, and it is that if you throw exactly the same experiment that we talked about, then without that extra phase, you throw something and you get it exactly at that point. If you go to very high energies, you can use the geodesics equation. But what this phase is telling you is that if you take account of that phase, then you get, instead of a peak at a certain point, which is this one, you get something that oscillates widely. And moreover, if you smear this here, then all of this goes away. So this is interesting because it means that features like UVIR mixing that we are used to from black holes, they already make their appearance here in this Euclidean setup when stringy effects are taken, where non-perturbative stringy effects are taken into account. But for us, all of this is basically just to convince you there are other ways to be convinced of that an observer at infinity sees two tails. It's not that you see only this tail, which is a very soft one, but you see also the other tail, which is related to this sine Liouville or a winding mode that drops much faster. And if you go to large enough energies, then for sure you will see this as well. So these are basically the way that we think about this now is that I and W are two tails, two semi-classical tails of the same state in the exact CFT. And this actually can be generalized, this FZZ statement. And it is, the generalization is interesting, and it will be very important for what I wish to talk about. So the generalization is basically a statement that every state that is localized at the tip of the cigar, at the very tip, this red point here, as a partner that is smeared all over the cap of the cigar. And again, semi-classically, you would think that these are two different states. But the statement is that these are different semi-classical tails of the same state. And basically one, to make it more precise, one cannot excite a state that lives here at the cap of the cigar without exciting its partner at the tip. They come together. Now I'm not going to discuss how we reached that conclusion, but I would like to state how we did this because it's going to be very important for the black hole case as well. So the reason why this is something that we did with David Kutasov as well, we reached that conclusion was that this realization that every state in the discrete representation of ADS3, it comes with a partner that is determined by the spectral flow, which was discussed by Maldacena and Doguri, I guess that in 98 or something like that, 99 maybe. So this is the case of the Euclidean that statement is a statement about the Euclidean cigar, and already here we have an issue with information in string theory, because you would think that this state and that state, they are different, but actually, well, it's the same state. So when we think about information theory and string theory, then we should take this into account. Okay, so we know that the tip of the cigar, this red dot here, if I do weak rotation, it goes to the black hole horizon. And we know that the cap of the cigar goes to what people like to call the black hole atmosphere, which is the region outside the horizon where excitations live before they can escape to infinity. So I've just argued that that string theory identify states that live at the tip of the cigar with states that live at the cap of the cigar. So you would think that that after weak rotation, the statement should be that states that live at the black hole atmosphere, like ordinary, massive states or massless modes that just propagate there, they are related to states that live at the black hole horizon. And this sounds very exciting because this is exactly the kind of thing that we would like to have, in which information inside the black hole is related to things that are happening outside the black hole. So this sounds very, very exciting, but there is a technical problem which I would like to describe now. So here is the problem. So normally in GR, the situation is that I have the cigar, and if I want to find the black hole, then I do this Artelocking story. I cut the cigar, I weak rotate, and I find a wave function. But now we said that on top of this, there is this winding mode. And we said that this winding mode must be there. We cannot evade this. So if I follow the same logic, then the winding mode must appear also in the Minkowskian section of the analytic continuation. Okay, so if this is the case, then the question is what is the description of this winding mode? So here we know that we have a winding mode, but what does it mean here in this Lorentzian section? Well, the standard answer that people like to give for many years now is that it becomes a gas of strings. And normally, well, so by that, I think that what people mean is that a gas of ordinary strings. Now, this doesn't feel right, and there are two ways to see this, one from the worksheet and the other from the target space, which I would like to describe. From the worksheet, if I just take the winding mode and I analytically continue it, this is what I get. So I start with an operator, I analytically continue it, follow Artelocking, weak rotation, whatever words you would like to use. This is what I get. But this operator is not mutually local with standard vertex operators that live in the black hole and carry energy. So how exactly do I do calculation with such an operator if I have this issue with a mutual locality? From the target space point of view, a gas of strings, if the right answer is a gas of strings, then a gas of string will fall into the black hole. But the winding mode remains outside. There is a tail that remains all the time outside. So how can it be that after weak rotation, I'll just have a gas of strings if they'll fall into the black hole? So what I would like to convince you is that this is not a gas of string. This is not the answer to that question. But the short answer is that the winding mode, after weak rotation, it becomes an instant folded string, which I would like to explain why I claim that. So there are two ways to see it. One way is from, if you want, an effective field theory kind of argument. And the other is using the exact CFT that we have for this SL2 modeled by U1 black hole. So let's start with the exact CFT. So there is an observation that was made by Giribet and Nunes, which is extremely useful to make this claim that I made here. And the observation is that the non-perturbative effects, the one that led Teschner, for example, to get this extra phase in the reflection coefficient, So you can get them using the Sine-Liouville potential, using the Sine-Liouville deformation, which you can think about as W plus F winding in one direction plus W minus winding in the other direction. But the exact same answer, the exact same result, Giribet and Yunis obtained by using a different operator. They used, if you wish, a fusion of W plus and W plus and W minus. And we refer to such an operator as F. Now, because F is a fusion of W plus, I have this plus here and minus here, then it is mutually local with ordinary excitations that live in the black hole. And these main obstacles that we have with the Sine-Liouville operator doesn't appear when thinking about F. And if I want to try to visualize it using the Hartel-Hawking-like approach, then as we said before, we have these windings, but pay attention to the fact that I have winding plus, let's say this direction, and winding minus. So basically, the statement from the target space point of view is saying that the two are combined to form a folded string that folds like so, and it fills the entire black hole. And this is the worksheet. So the statement is that if we go back to the mother SL2 theory, then W plus and W minus are singlets of the SL2 left times SL2 right, and so is F. And what Nunes and Giribet did was to use these singlets of the representation to get all the non-perturbative effects, and this is how we think about the relation between the winding and the folded string from the target space point of view. Yes, so as I said, so you see that the folded string is folding towards the black hole, and so it fills the entire black hole, and this is what I said before. Okay, so let's go back to the statement that I made in the Euclidean case and see what is the analog statement now in the Lorentzian case. So in the Euclidean case, we concluded that I, which was the formation that formed the cigar, comes with a condensate of the winding mode, and we said that these are two components of the same state. And now we have the same I, or the weak rotation of this I. Condensation of this I will get the black hole. So if I start with flat space with a linear dilaton, I condensate that I get a black hole. But when I do so, I must also condense F, this folded string operator that fills the black hole. And again, the statement here is that these are two components of the same state, so I really cannot condense I without condensing F. They come together. Now, before I talk about the other way of seeing that there must be folded strings behind the horizon, let's keep pushing this spectral flow logic and see what we can say about excitations of the black hole. So if I just look, on the usual tortoise-like potential in the SL2 modeled by U1 black hole, then the potential looks like so. So this is the horizon, the potential, let's say, goes to 0. Then at infinity, the potential goes to q squared or 1 over k. There is a certain mass gap. Now, there are excitations that live in this potential. So, for example, the purple line is an excitation that goes from the horizon all the way to infinity. I can also think about excitations that fall towards the horizon from infinity. But there are also excitations that are semi-infinite. So they come from the horizon, they hit a certain point, and then they fall back. So the spectrum here is clearly, the purple spectrum is clearly continuous. The red spectrum is also continuous because the horizon is really at minus infinity in this coordinate. But despite that, from the mother SL2 point of view, the purple line sits in the continuous representation, while the red line sits in the discrete representation. So I remind you that what fixes that is not whether the spectrum is continuous or discrete, but really what is the difference between the dimension and the other quantum number, m or m bar, in the SL2 representation. So, but leave aside technical things. The upshot of all of that is that these guys, they sit in the discrete representation of SL2, and these guys in the continuous. And like we said, the argument that gives a partner to this guy, a partner, or if you will, a stringy partner to an excitation, to a GR-like excitation, is the fact that it sits in the discrete representation. It just follows from the algebra of ADS3. So, so the conclusion is that every GR-like excitation that lives here comes with a partner which is which follows from it via a spectral flow. And if I want to think how it looks like, then this excitation, if we use Penrose diagram, so that excitation I can, so this is just a GR excitation that comes from the horizon, reaches a certain point, and then it falls back to the horizon. So it comes from the horizon, reaches a certain point, it falls back. Now, the statement that it comes with a partner means that whenever I have such an excitation on top of the black hole, I must excite. Also, this is a bad way of drawing an excitation. I must excite the folded string that fills the black hole. Now, so it feels a lot like ER equals EPR of Maldacena and Susskind, because you see, every excitation that lives outside, it feels like a stringy realization of this idea, because each excitation that lives outside comes with an excitation of something that lives inside. But there is a twist to the plot, and the twist is that the black hole is not empty. It is filled with folded string. So in this picture, I really the excitation is of something that is there. So it's not that I have an empty black hole, but I have things there, and I excite them. this sounds very strange, and if there is any chance that I'll convince any of you that this is correct, then I should be able to explain how come that there are folded strings inside the black hole. Okay, so the argument that I gave so far was a story about spectral flow in ADS and discrete representations and things like that. But this, it feels like there has to be a much more down-to-earth argument why that statement that the black hole is filled with folded string is correct. Well, if it is correct. So this is what I just said. Can I understand this from the low energy perspective? And if I can, then I should be able to answer the question, how many folded strings are inside the black hole? And I would like to start now with a discussion about that. Basically, what I will try to present is an argument which does not rely on any algebraic structure of the SL2, why there has to be folded strings inside the black hole. So the story, so the starting point for that story, I'll start with a linear dilaton background. So I have here, now R is the linear dilaton direction. I have, you know, the string coupling depends on R, and I have a trivial time direction in the problem. So the string coupling blows up when R goes to -infinity. And we all know that the Q affects the perturbative physics. It does so at the length scales of the order of 1/Q. So we care mostly about Q, which is small. So the effect of this is that the length scales that are much larger than 1. Now, but so this is well known. Something that is less known is an observation that was made by Maldacena, I think in 2005, that this linear dilaton leads to a non-perturbative, in the sense that I'll describe, a solution or a semi-classical configuration that is simply absent when Q vanishes. So what I would like to do is to talk about this configuration of Maldacena and see what it means for the black hole. So this is this new classical solution that he found. So, well, the details are not terribly important, but this picture should tell the story. So I have, this is the strong coupling regime, this is the weak coupling, and this, and then I have a folded string that, well, so sigma starts with, so I start at infinity, I run, I reach a certain point, which is the tip, if you will, of that folded string. I keep increasing sigma, and I go back to infinity. So I do that at every point, and I end up having this long string, this folded long string that fills all of this region here. Okay, so the Maldacena's motivation was very different than what I wish to discuss. So I'm not going to describe his motivation at all. I just want to take from his paper this, if you will, technical observation that there is a classical long string solution that is absent when Q is 0. So there are several properties. First of all, we see that this folded string, it folds away from the singularity. And the length scale here of the folding and of the turning, the length scale, which is the interesting length scale, is very small. It's of order Q. So in that sense, this is a non-perturbative configuration because it's tiny compared to 1 and compared to 1 over Q. So the folding is a local thing that is happening at scales of order Q. So if I think about the black hole, then it might be more difficult to find, the analog of this exact solution. But how it should look like, then it's simple to visualize. Well, I can have, so this is the eternal black hole, the SL2 modeled by U1 black hole. And I can have a folded string that folds like so. It folds away from the singularity towards the weak coupling. I can have a larger one here. What I cannot have is a folded string that folds towards the black hole. I cannot have such a configuration classically. Now, what happens behind the horizon? So behind the horizon, if I go here, so here I have locally a space-like linear dilaton. If I go to this region, then behind the horizon, I have a time-like linear dilaton. So I can approximate a patch behind the horizon by a configuration like this. And then it's a simple manner to basically analytically continue Maldaceno solution, and you find that solution. Again, the details are not important. What is important is to see how it looks like. Now what happens is that if the strong coupling is at the future, then the folded string is folding towards the strong coupling. So you start here, you go like so, each time you end at the blue line like this. So this is how you would think about it if you wish to use tau and sigma, which were natural in the space-like case. But if you think about the physical process that is happening here from the target space point of view, then you see that at this point in space-time, what is happening is that a closed folded string is created. So it is tiny at the beginning, then it becomes larger and larger and larger and larger. Okay. I don't have time to discuss it here, but the total energy of that configuration vanishes, which is why it is possible for this to happen. So this is something that I really don't think that we have time to discuss. The main point is that this is something that happens locally, and it happens classically because it's not like a Schwinger process. There is no, so this is a classical solution in Minkowski spacetime. I don't have to glue a classical configuration to some, a Lorentzian configuration to some Euclidean section like in the Schwinger process. All of this happens in Minkowski spacetime. So the production rate here must be very large. And I think that we know something that I'm doing with Aki Hashimoto, what is exactly the production rate, but it's not terribly important right now. So the statement is that folded strings are created classically behind the horizon. And if I go back, it might take me a bit of to this picture. Where was it? No, sorry. to this picture, then what we see here is the quantum tail of the folded strings that are created classically. So here, the folded string behind the horizon, they are created classically. And this is just a quantum tail of them that manage to penetrate behind, well, outside the horizon. Let me go back to where I was. Oh yes, sorry, I prepared this already. So this is what I wanted. I apologize. Okay, yes. So so if there are folded strings behind the horizons, then I should be able to tell you how many of them are there. And a direct calculation is something that hopefully will manage to do in the near future. But what we did with Uri Peleg was to find an indirect or three indirect calculation to calculate the number of folded strings in the black hole. And I want to describe them and see so I'm not going to describe the details, but just how you do it. So basically, the trigger for the creation of the instant folded strings is to have a time-like linear dilaton, which grows with time. But the back reaction of these guys is to suppress it. So you can ask yourself how many instant folded strings are needed to kill the slope of the linear dilaton. So this is one way of estimate or of calculating how many of them should be there. Another one is a more tricky one. So they have a very funny back reaction. I don't have time to go over it, but the very fact that they managed to keep on growing after being created at the point means that they violate the ANEC, the average null energy condition, which is to say that their back reaction is very should be non-trivial, and indeed it is. In fact, if this is a folded string, and this is an infalling particle, then the back reaction of the folded string will be, so suppose that you hit it at some v, then it will push you back in time a certain amount that is linear with that v. So the further you hit the folded string, the further it will, the more it will push you back. And it will also twist, or it will also boost the infalling particle. So if the particle was supposed to follow this dashed line, it will be boosted like so. So then you can ask yourself, how many folded strings do I need to have so that I can never penetrate this region? Namely, I hit that point and I reach this point with an infinite boost, so the excitation keeps on propagating on the horizon. And similarly, if I go like this, I will go like so. So this is a different way to calculate the number of folded string. Another way is to use entropy consideration. This is not entropy consideration the way that we think about them in statistical mechanics. So this is the reason for the quotation mark. We ask how many folded strings are there, and we declare that the entropy is k times this because of some reasons. I don't want to go into all of this. But the upshot of this paper is that if these three ways of estimating or of calculating the number of folded string, they give the exact same answer, which is this, the one that is given here. It's 2 pi over k, the level of the algebra, times the string coupling at the horizon. Now I should say that these two, the considerations here, they really follow from low energy effective action. Don't need to know any exact CFT story, but this entropy consideration really requires some exact CFT discussion that I'm not going to do here for obvious reasons. But the nice thing I think about that is that you have here three different ways of calculating this number, and the three different ways they give the exact same answer, which seems to be just a fact. Okay, so let me conclude. So my main conclusion from working on this model for many years now is that string theory is a smart theory, and the best thing that I can do, or my working strategy basically, is, like I said, to try and listen to what the theory has to tell us. And in that case, it includes instant folded strings that really have no point-like analog. So these are creatures that exist only in string theory. They don't have a counterpart in particle physics. And what is nice about them is that they make their appearance, at least in that case of the SL2 modeled by U1 black hole, exactly when needed. And we see this both from the exact CFT point of view and from the effective action. So I think that I'll stop here.
Okay, thank you, Sunny, for the interesting talk. We have still some time for questions. I can start.
Okay.
So this is a very naive question. So what new perspective does this observation offer with regards to the information paradox? Can you recover the information that is contained in these folded strings behind the black hole horizon? What is the statement?
Yes, so well, the statement, so if I want to be bold, is that the region behind the horizon, so this is basically the main picture that is relevant. If you have enough folded strings behind the horizon, then you cannot penetrate the horizon. So here you are, you try to fall into the black hole, but the folded strings, what they do, because of this funny feature that I didn't have time to discuss, their energy momentum tensor, they prevent you from doing that. So they manage to keep all the information outside.
And what happens when the black hole evaporates then?
Yes, so the way that the black hole evaporates is that, so this is actually, so this is very, so this picture is very important for that, because, yes, so classically, this is the story that I told you. But as I said, quantum mechanically, there will be a tail of the folded string which goes outside the black hole. Mm-hmm. So once this happens, so you see that classically here, the folded string is folding in the wrong direction. because Maldaceno's folded string are folding in this direction towards the weak coupling. So this region is a space-like region. So what will happen is that when you take G-string effects, and this is so I'm not sure that I know how to write here. So at any rate, so when you take G-strings effect, then what can happen is that this string will basically because of the string coupling, it will form here a closed string, because you can fold in this direction. So you can form here a closed string, and this closed string will be emitted from this folded string. So you have a large folded string. So maybe is it okay if I'll it might take me just a minute to
sure
to log into my how do you call it, this thing, and then there is a nice story here, and it's qualitative. I apologize for that, but I think it is still interesting. But I see that this is going very slow, so maybe I'll manage to draw something. Okay. Where? So let's see. So I'll stop. Well, technology, whenever you really need it, collapses.
Yeah, it's okay. If you want, we can go back to the presentation, and if somebody else wants to ask a question, well,
I can. Okay, let me attempt to do something different. So what should I do, really? I guess that I can open. Yes. So let me. I think that here I can do it. So let's do it. It won't be as this. I think I can do.
okay.
Let me. Well, did you? So let's do this, and let. Now in this mode should be able to draw something. Wait, what am I doing? Yes. No. Sorry. Yes. So this is the horizon. Here strings are created like that. They fall toward the singularity. There is a quantum tail that folds like so. Okay, quantum. So in a space-like region, a string can fold in this direction. But quantum mechanically, it can fold like so. This is this tail that we talked about. Now, quantum mechanically, so let's have a large one. You can imagine that there is a process in which this folds like you interact like so, and then this goes all the way to infinity. This then will escape to infinity. Now, this is the way that the folded string radiates, and you can estimate, this is a very naive estimation, but you can estimate what is the rate of this radiation. This is something that Amit and I did, and at least for very large energies, it seems to fit with Hawking's temperature. So this is how the radiation should look like in this setup.
Okay.
But this is very qualitative, so because we don't have a good understanding of the model at the finite G-string level.
Okay. Okay. Thank you. More questions?
Yeah. So so the usual conventional wisdom is that this sort of winding condensate is harbinger of Hagedorn physics. And you know, one might have said, well, you're in Euclidean space, you're doing some kind of angular quantization, which means that you're essentially doing working in Schwarzschild time in the geometry. And so, you know, a Schwarzschild, an observer traveling Schwarzschild time like geodesics would indeed see a finite temperature which grows as you approach the horizon. So, and the onset of this stringy condensate you're talking about is precisely where the local temperature reaches the Hagedorn temperature.
Right.
But you seem to be presenting a very different picture of this condensate, and I was wondering if you could comment on the relation between these two pictures.
Yes, so right, so the question indeed is whether, so I think that we all agree that at infinity there is this tail of the winding mode. And now what you're basically asking is how seriously one should take the wave function of the winding mode when you approach the horizon. And I think that so I think that, you know, there are two answers to that. One is that, you know, we can argue endlessly about the two possibilities that you mentioned, but I think that the fact that classically folded strings are created behind the horizon because of the time-like linear dilaton is a very convincing argument why there is something there. So it's not it's not just a matter of choosing a coordinate system and I see a local temperature and I reach the Hagedorn temperature, etc. There is something there, and this picture, where is it? So maybe it's this one. Yes, so this picture I think suggests that well, there is an actual effect that happens there, and we know that F, or we know that there are non-perturbative corrections to the, for example, to the scattering amplitude, and we know that they are quite non-trivial. And if you ask yourself what is the target space explanation of that, then I think that story that is related to this work of Giribet and Nunes goes very well with this classical observation that folded strings are created behind the horizon. So I think that there is need, of course, there, you know, one can study this. You know, you can go to 3-point function, you can ask many questions. I'm not saying that this is a done story. All I'm saying is that the story here has a support from different directions that didn't have to agree.
And once you stuff these strings behind the horizon, so the particular solution you looked at was basically just a straight folded string, right?
Yep.
Presumably there are additional solutions where the folded string has some transverse excitations on it, or
Yes.
is that not allowed?
Well, it's a right. So now, so this is so yeah. So if you allow excitations in other directions, then for sure there are. If you restrict yourself to the two-dimensional case, then there aren't. But you can imagine folded strings that interact. So you can have wiggles like that, which are which will cost some energy, and you can so all of this is really a very premature statement that I'm about to make, but I think that that if you count correctly, and how to do it correctly, this is the big challenge. If you count correctly the excitations of these folded strings, then you should account for the Hawking-Bekenstein entropy. So what I'm trying to say is that what Amit and I did with my student about this entropy in quotation mark consideration, it can be done just like in statistical mechanics, I believe, which is related to what you're asking. And I'm optimistic that one should get exactly the Bekenstein-Hawking entropy. But maybe I'm just.
So the claim is that that many strings at the bottom with a Hagedorn entropy on each one will account for the Bekenstein-Hawking entropy.
Right. So the Bekenstein-Hawking entropy is 2 pi over G string squared in this notation that I'm using. So basically, so if each folded string is made out of k well, gravitons or whatever you like to call them, then you get that the black hole entropy is the number of excitations. But you want to do better than that. What you want to do is to really do it the way that we do it in statistical mechanics and see all these excitations as different states and just count the number of states, and we are still not there. So there is a big challenge, but I really think that we are heading in the right direction. So I didn't have time to discuss at all the work with Aki, but some of the things that we are doing there are very helpful. I think that that could lead to development exactly along these lines, but we are not quite there yet.
Okay, thanks.
Any further questions? Doesn't seem like it. So I would like to thank you again, Sunny, for the very interesting talk.
It was my pleasure. Thank you.
Thank you.